Hello. In this video we're going to take a look at Fourier decomposition of functions in the particular case of the infinite potential well. So we showed in a previous video that the eigenstates in the infinite potential well, the energy eigenstates, are orthonormal. In fact, there's a stronger condition. The energy eigenstates in the infinite potential well form what's called a complete orthonormal basis. What we mean by this is that any arbitrary function of position within the well can be written as a sum of different energy eigenstates. Just clear the board. Okay, so mathematically what we're saying is this. That is, an arbitrary function f of x can be written as a sum from n equals 1 to infinity of phi nx, our energy eigenstates, the infinite potential well, multiplied by potentially complex coefficients fn. It's a form of Fourier analysis. In fact, again, it's not just eigenstates for the infinite potential well. This occurs in a much broader class of cases in quantum mechanics, and we'll take a closer look at the cases it applies to when we come to do matrix mechanics later on. For now, you can think of it in a very close analogy to expanding an arbitrary vector in an n-dimensional vector space in terms of the n basis vectors in the space. We'll see that that analogy is indeed very close later on in the course. For now, in order to make this useful, we need a method of solving for these complex coefficients fn, and we can do that quite simply using the orthonormality of the energy eigenstates. So we can write this following. We can multiply from the left by phi m star of x, and then integrate from minus infinity to infinity. In fact, this will only go over the well because the phi m's are 0 outside of the well. And when we do this, on the right-hand side, we have the following. So we've multiplied by phi m star in from the left, and then we've integrated dx. The phi m star can pass through the sum, and the integral dx can also pass through the sum, that's because sums and integrals commute. Fn are coefficients to be determined, but they're not a function of x, so they can come outside the integral. And so this quantity here, from our orthonormality condition, is just the Kronecker delta, which is 1 if m equals n and 0 otherwise. So when we sum over the n's, the Kronecker delta selects out the case that n equals m. Every other term is 0. And so this expression over here reduces to the following. That is just f subscript m. So overall then, if we just switch, let's swap the sides of these two things and switch the label m to n, and we have the result. So we can write any arbitrary function f of x, which lies within the same boundaries as the infinite potential well, as a decomposition of energy eigenstates in the potential well, and the coefficients we use in that expansion we can determine from this simple formula here. So this is already very useful. It's as useful as Fourier decomposition, of which it's an example. A particularly important use of this is that we can specify some starting wave function, so it doesn't need to be an eigenstate. Say we prepare a state which is, say, a position eigenstate in the well. We identify the particle at a particular position. Or we can put in general quite different wave functions in the well, depending on what types of measurements we made and so on. If we prepare them, we're only specifying, or we can prepare them by specifying the amplitude at each point in the well. But then we'd like to know how the wave function varies with time after that. Now, the time-dependent Schrödinger equation should tell us the time evolution of any state, not just energy eigenstates. And this is how it does it, because remember, the time evolution of the energy eigenstates is trivial. We know how to solve this. And so we apply the same reasoning here, and we find that starting off in f of x at time t equals 0, the result for f of x at later times is as follows. Okay, so specifying the wave function at an initial instant, we know its behavior for all future times because it must obey the time-dependent Schrödinger equation, so it's dictated. That is provided no measurement is made of the system. Measurement is very strange, as we'll see shortly. So we specify our arbitrary function of position, its time evolution, we work out by decomposing it into energy eigenstates, each of which we know the time dependence of, and it takes this trivial form. The time dependence of the state itself need no longer be trivial because we're summing up different energy eigenstates here. In fact, this is a general expression of quantum superposition, which we'll take a look at in the next video. Thanks for your time.